Hello everyone, welcome you all to the third session of Statistics for AI and Data Science. In this session, we are going to study about Gaussian normal distribution and its PDF. So let's start. One of the most important ideas in probability and statistics is the concept of distribution. Distribution. We will understand what a distribution is by using one of the most famous distribution called Gaussian distribution, and we will understand it. So let me draw first one shape. If I draw a shape something like this, so I have drawn this shape. So you might have come across a shape like this, which looks like bell-shaped curve. So this looks like bell-shaped curve, right? This is one of the most recognizable shapes in probability and statistics and stats. And by the way, we saw such a shape when we were looking at probability density function of Setosa, versicolor, and virginica when we were studying exploratory data analysis of iris flower dataset. So let me show you again for your better understanding. This is a PDF of the petal length of iris flower dataset. So if this is my petal length, the probability density function of petal length of Setosa, versicolor, and virginica flowers actually look like this bell-shaped curve that are very, very representative of a Gaussian distribution. So the Gaussian distribution is very popular distribution that is used extensively in statistics, and we will learn everything about it one by one. The bell-shaped curve that you see is basically the probability density function of a Gaussian distributed random variable, of a Gaussian distributed random variable. So let's assume X is a continuous random variable. So what is X? X is continuous random variable. So if X has a PDF, if let's say X has a PDF, probability density function, which means a probability density functions look like bell-shaped curve. Look like this bell-shaped curve. Then we say X has a distribution which is a Gaussian distribution. X has a distribution which is Gaussian. Fine. Now you might ask, why should I learn about this distribution? Because a lot of things in nature actually follow Gaussian distribution. Not everything, but certainly some very important thing in nature. Let's say, for example, height of the people, weight of the people. These things tend to follow a Gaussian distribution. Similarly, this petal length also follows the Gaussian distribution, which are actually measurements of petals of a real flower. If you look at the sepal length, it will also look like a Gaussian distribution. They all seem to look like bell curves. We will see whether they are Gaussian distributed or not little later, but for now, they all look like bell-shaped curve, right? So Gaussian distribution occurs a lot in nature, especially in natural phenomena like height and weight. It is also connected to a very important idea in statistics called central limit theorem. Central limit theorem. We will look at the central limit theorem a little bit later, but just take my word for it right now that it's extremely widely found distribution in nature. Having said that, now you might ask, why do I learn about these distributions? We will see why we are learning about distributions after we learn some properties of distribution and how it is useful. But in short, I could say that distributions are very simple model of a natural behavior. Distributions are very simple model of natural behavior. Natural behavior. Fine. For example, if you tell me that the petal length of, let's say, Setosa flowers follow Gaussian distribution, I can tell you a lot of properties about the petal lengths without having measured any one of your petal lengths. So it's a very simple model to summarize all the information about the random variable or a physical measurement like length, weight, petal length, sepal length, etc. Everything can be thought of as a continuous random variable. So these are my continuous random variables. We have already discussed continuous random variable in the previous session. So by the end of this subtopic, you will understand everything about distribution. There are a lot of interconnected areas that we need to cover first. So one by one, slowly, we will cover it. Then at the end of it, we will get the whole picture. So let's understand Gaussian distribution in a very elaborate manner. The curve that you are seeing on my screen is basically a Gaussian distribution. So Gaussian distribution is also called normal distribution. Gaussian distribution is same as normal distribution. Normal distribution. Fine. Pardon me for my handwriting. We will see what is a standard normal distribution in a while. So in this plot, if you look at this plot carefully, if x is a continuous random variable, so this is your probability density function PDF. So your probability density function of your Gaussian random variables look like this small hills, all your bells, right? So if you look at the top right corner here, you have a very nice legend which shows you two values, mu and sigma square. So let's take the blue curve first. So I am considering this blue curve here. If you consider this blue curve, we know that we have already learned the concepts called mean and variance. V-A-R-I-A-N-C-E, variance. For a Gaussian random variable, mu is nothing but the average value or the mean value, and sigma square is basically the variance. So this sigma square is basically my variance. So if let's say, if this x behaves like a Gaussian distributed random variable, if x behaves like a Gaussian distributed random variable, then if the mean is 0 and its variance is 0.2, then its PDF will look exactly like this blue curve. dark blue curve. Fine. There is a very interesting thing here. If you tell me that your random variable x follows Gaussian distribution, and if you give me its mean, that is 0, here the mean is 0 at this point, this is my mean, and if you give me the variance, variance is basically what? Variance is my spread. We already understood this is my variance and its value is, let's say here, 0.2. So if you give me its mean and variance and nothing else, you just give me these two values, mean and variance, I can tell you what its PDF is. So these two values, mu and sigma squared, that is variance, are called parameters of the distributions. So these two values are called parameters. What are my parameters? Parameters of distribution. Distribution. What are the parameters? Mu sigma square, comma mu. So these two things are called the parameters of the distribution. Let me show you something more profound. Let's look at this data for a second. So I have my random variable as petal length here. So imagine if somebody tells me that this setosa flowers have a mean of, let's say, 1.5. I'm taking this point as 1.5. That is, I'm taking mu is equal to 1.5. And let's say the variance seems to be very small here. So let's take the value of variance, that is sigma square is equal to 0.25. And let's assume that this setosa's petal length follows Gaussian distribution. This is all assumption I am making right now. The moment you tell me that mu is 1.5 and sigma square is 0.25, I can quickly draw the distribution, this distribution, without having even seen one value of petal length of setosa. So if you just give me these two values, I know what the PDF looks like. This is basically the PDF. Now, as soon as I know how PDF looks like, I can compute my CDF. CDF is cumulative distribution function, right? So all the information that is there in here, the observation, here we have a 50 observation in case of iris flower. So all the information that is there in 50 observations of iris flower data set can be summarized very succinctly by using these two values. On the other hand, if I don't know whether my random variable x is Gaussian distributed or not, here in this case, your petal length is Gaussian distributed or not, let's say, if you do not know, then these two values have no significance for me. So the first thing that we need to know is whether my petal length is Gaussian distributed or not. If this thing is true, if my petal length is Gaussian distributed, then all I need to know to plot its PDF is just mu and variance. Now let's see how the shape of the Gaussian distribution changes as mu and sigma square changes. Fine. So if you look at these three plots over here, this blue plot, this red one, and this yellowish plot over here, all of them have a mean of 0. And the variance of your blue plot is 0.2. So let me write here 0.2. This is my variance for this blue. And the variance of this red plot is 1. So let's say this is the variance of my red plot, which is 1. And this is the variance of my yellow plot, which is 5. Let me write the variance of my yellow plot. This is 5. So we do know that variance is basically a measure of spread. Variance is basically a measure of spread. Spread, R-E-A-D, spread, or you can say scale. scale. So we do know that variance is a measure of spread. It's also called a scale in probability and statistics. So if my variance is small, then my probability density function, my PDF, is going to be picket and thin like this. Can you see? As my variance increases from 0.2 to 1, my probability density function is going to get fatter and fatter and shorter and shorter. That's what happens if your variance changes. Now, what about mu? If your mu changes, and if you can see from this PDF, from this red curve, when you come to this yellow curve, this PDF is, my variance is changing by 5 times. So this is much more fatter than this curve. This yellow curve is much more fatter and much more shorter than this red curve. So that's what happens if your variance changes. Now let's talk about mu. If your mu changes, what is my mu? Mu is basically my mean values. Mean values. In this case, all the three curves is having the mean of 0. So if your mu changes, so for this green curve or green line over here, your mu is at point -2. This is my mean for this curve. Mu is equal to -2. And this is the peak of my hill in probability density function. So the peak of hill in probability density function is exactly at mu. This is a point to note it. The peak of the hill in your probability density function is exactly at your mu. Here also, the peak of the hill of your probability density function of a Gaussian distribution is exactly at mu. So mu is the most often found value in PDF. The height represents how often we find these points. So in a Gaussian distribution function, the peak of your hill in your PDF is at mu. Fine. Let me plot a Gaussian distribution with mu is equal to 2. So let's plot a Gaussian distribution with mu is equal to 2. If I join this, so if I plot a PDF like this, and if I know that it's a Gaussian distribution, it follows a Gaussian distribution. So since this is the maximum value at this point, immediately I know that my mu is equal to 2. Fine. So let me give you some simple notations. Since we know that the parameter of the Gaussian distribution are simply mu and sigma square. These are called the parameters of a Gaussian distribution. Let me write it here. Parameters of a Gaussian distribution is mu comma sigma square. Sigma square is my variance, which means that if you just give me the mean and variance, I can tell you everything about the probability density function of a distributed random variable. Now let me introduce you to some notations. Let's assume x is a random variable. I say that x follows a Gaussian distribution with mu and sigma square. So a Gaussian distribution or a normal distribution with mean, mu and variance sigma squared. So how to read it? So this is my x. This is called follows. This is called follows. This is my n represents your normal or Gaussian distribution, normal or Gaussian distribution. And what are the parameters of my distributions? So here mu and sigma square are called parameters of my distribution. So if somebody says X is normally distributed, now let me tell you something else. So if somebody says X is a normally distributed with mean 0 and variance 2. As soon as I see this, I can plot the probability density function PDF of X with mean at 0. So let me plot this first. So I have plotted the probability density function of X with mean at 0. And we will see how variance plays in this. Your variance probably will be, let's say, this is my variance. This thing will be my variance. And let's say this is -2. This is my +2. And take this is as -4, this as +4. Now we will see how to get the shape. So is the bell shape more understandable? The peak of the bell shape is always at mu. Here my mu is 0. Fine. And this is my peak. Let's just again take a quick example here. Let's assume you have another random variable called y. First, I have taken this random variable x and I have plotted this plot with a mean of 0. Now, let's assume that I have another random variable called y. This random variable also follows Gaussian distribution with mean 0 and variance of, let's say, 4. Then I know that my x is like this. This is my plot for the x. And I know that my x is like this with a mean at 0. So if my x is like this, then my y would be fatter and shorter. Why my y would be fatter? Because y also has a mean of 0 and it has a higher variance. So if I will plot it, I will get something like this. Then I know that my x is like this. This is my x. So if my variance is higher, so my y would be something, let's say like this. And this is the variance for y, which is in this case 4 here. So if x is like this, then my y would be fatter and shorter because y has a higher variance than my x. Variance basically talks about spread. So this spread is much more than the spread of the random variable x. This is my random variable y and this is my random variable x. So having understood this, let's go into some more mathematical details of the Gaussian distribution. We have seen the graphical part of it. We have understood the bell-shaped curve. Let's go into slide details of math. Let's assume x is a continuous random variable. If I know that x is a continuous random variable and x is, let's say, normally distributed with a mu and sigma square. X could be anything, maybe petal length, maybe sepal length, maybe height, maybe weight, etc. Any variable. So if x is normally distributed with a mean of mu and variance of sigma squared, then I can quickly say that the probability density function of x equal to some, let's say, probability density function of x equal to some, let's say, small value, small x. Remember, here, this capital X here is continuous random variable, and this is my value. This small x is my value. So let's assume if x is the is a height of a student. Let's just assume for a y, if x is a, let's say, height of a student. Height. And let's say it's equal to 160. I'm taking any value 160 centimeters. So this is my actual value. That's why I wrote it in small x. You can write it as an expression like this. So probability density function of a random variable x being equal to small x, this small x would be 160 centimeters or something like this. So this is a random variable capital X. In statistics, a normal distribution or Gaussian distribution is a type of continuous probability distribution for a real valued random variable. The general form of the probability density function is something like this: 1 by root 2 pi sigma exponential minus of x minus mu square by 2 sigma square. This is my exponential. This is exponential of x is equal to e power x. This is what means. This parameter mu is called the mean of the distribution. Also, it's called median or mode when it's applicable. While this parameter sigma here, this parameter sigma is its standard deviation. Standard deviation. And my sigma square is, this sigma square is basically my variance. This is my variance. This sigma is my standard deviation and this is my variance. So a random variable with a Gaussian distribution is said to be normally distributed and it's called normal deviate. Normal deviate. Of course, this looks very daunting on the surface, but I will simplify this for you. I will break this up and explain it piece by piece. So let's go and understand what is this expression here. So here exponential of this thing is nothing but e raised to the power x. This whole expression is nothing but e raised to the power x because it is a exponent. So it's an exponential function where e is my natural base because it's harder to write this whole expression in this superscript. So we typically write it in this simple way. So we can simply write this exponential to the exponential of this whole expression by e raised to the power x. So you must have encountered this in your high school when you were learning logarithms. So to understand this function, let's simplify it. Let's assume my mu is equal to 0 and my sigma square is equal to, let's say, 1. This is assumption I am making. So if sigma square is 1, then my sigma is equal to 1. Let's just assume this. So as to simplify and understand the math, what I can write it here? The reduced form of the equation. If I consider this whole expression as, let's say, x, then I can write it like this. Px is equal to 1 by root 2 pi. Sigma is equal to 1. So this is nothing. Then this will be exponential of, let's say, minus 1 by 2 x square. If you look at this carefully, you will see that this whole thing is a constant. This thing is also a constant. So if I have to simplify this further, I can write it like, since this is my constant, this is also my constant. So I can write y is equal to here exponential of minus x square by 2. So what I have done here is first I have written this very crazy looking formula here. Then I have simplified it by making mu is equal to 0 and sigma square is equal to 1. I am further simplifying it by removing the constants. So since this is a constant, so I have removed the constant. If I have to plot the shape of this function, what is the shape of this function? Because by just removing constant, the form of the equation still doesn't change. When you plot this function over here, what you get is your well-shaped curve only. Let me explain you what it is. So this can further be written as exponential of minus x square. This is my final equation. I have removed the constants, both the constant, this constant and this constant. Fine. Now let's plot this curve. Let me explain you what it is. So your mu, of course, is 0. This is my 0. And what it says is, this is your x. So your mu equals to 0, right? This is my random variable, let's say x. Let's assume this is my y, which is nothing but probability density function of x. So your y is nothing but p of x. Fine. Now what it's saying here is this: as x increases, this is extremely important. As x increases, let's say my x is 0. Initially, let's say my x is at this point, x is equal to 0. Fine. At that point, I have at this point, when my x is equal to 0, I have a very high value here, that is when I will put, let's say x is equal to 0, I have a very high value at this, which is 1 by root 2 pi, correct? At x is equal to 0, my y is extremely high. If my x equals to 0, what happens to y? If my x equal to 0, it's e raised to the power 0, because here e raised to the power 0, which is equal to 1. So y is going to be e raised to the power of 0 with these constants put in. So I will put in the constants here. What I will get? I will get 1 by root 2 pi exponential of 0, which is equal to 1, because exponential of 0 is 1. So the maximum value here in this case, with mu equal to 0 and variance is equal to 1. Let's assume my sigma squared is equal to 1. And the maximum value here is going to be 1 by 2. Just let's drop the constant to get better understanding of the shape here. So what it's saying here is, what is this? What happens as x increases? Let's understand what happens to y as x increases. As I am moving here on this axis, as the value of x increases, my y is going to reduce. Because this function, if you just look through this function here carefully, as x increases, what happens as x increases? Your minus square, this minus square is going to reduce because it's a negative. First thing is that as my x increases, my minus of x square is reducing. Then the second thing is that as my minus x square reduces, exponential of minus x square reduces. As x moves away from 0, your y is going to reduce. As you can see in this plot, my y is getting reduced. As x is increasing, my y is getting reduced. Now, this is my first observation. Now, in the first observation, let me write something. as x moves away from mu, y reduces. This is my first observation. Now let's look at the second observation. What is my second observation? My second observation is as x goes away from 0, even on the negative side. So what happens if x is equal to 2 here? So it doesn't matter whether x is equal to 2 or x is minus 2, because what we have is minus x square. Because what we are having minus x square. Since it already has a minus x square, so it doesn't matter whether x is positive or negative. X square is going to be the same value. This component is going to be of the same value. Fine. Which means whether you have x equal to 2 or x equal to minus 2, the value is going to be exactly the same, right? Which means this function is symmetric. This is my second conclusion. So this plot or this function that we just saw is symmetric, right? So this is your y and this is your x and this is your mu equal to 0. It is symmetric because whether you take x equal to 2 or x equal to minus 2, we are going to get the same value in this function here, right? So this function we have here is, I will just write it here, probability density of x equals to y. We can simply write here probability density function of x equals to y, which is nothing but exponential of minus x square. Again, this is the simplest form. I am trying to explain you the bell-shaped curve here, right? Now, the third conclusion is, now we know that if you look at this curve, the third thing is, now we know that as we move away, my y is reducing. But how fast does y reduces? This is my third thing. Remember, y is not just reducing. Let's say if y was exponential of minus x square. So what does it mean? It means that it's going to reduce exponentially, because here y is exponential of minus x square. So what is exponential of minus x square? It's nothing but 1 by e raised to the power of x square, right? Which means as x increases, our y is going to reduce because it's 1 by exponential of x. But what we have here is exponential of minus x square. Let y is equal to exponential of minus x, which is equal to 1 by e raised to the power x. So p raised to the power x is equal to 1 by e raised to the power x square. You can also write it this thing, or you can simply. Let's understand something very important. When my x is increasing, why my y is reducing exponentially? Because we have a square term over here, correct? So it's actually reducing extremely fast here. It's reducing really fast, which you will notice better when you will see this curve. So let's see this curve. If you look at this curve over here, this is very important. So let's look at the blue plot over here. So this is very important. Let's look at the blue plot over here, right? So let's say this is x is equal to 1. This point is my x is equal to 1. What is the value corresponding to y? This is my y. This thing is my y. So what is the value corresponding to y when x is equal to 1? So if I will come, this is, let's say, this is the point. Fine. So we have roughly a value close to, if you will look at this y, we have roughly a value close to 0.1. So this is basically, let's say, 0.1. Fine. So at x is equal to 1, we have a value of y that is equal to 0.1. At x is equal to, I can write it here. Let me write at x is equal to 1. I have y is equal to 0.1. Fine. For this dark blue line. But as soon as x goes to 2, let's see this. As soon as x is going to 2, as x is equal to 2, y value almost have reached 0. Can you see the y? This has almost reached 0, which means it's falling extremely fast. So this bell-shaped curve actually is reducing exponentially with quadratic function here, right? It not just reducing exponentially, it's reducing with a quadratic function inside it, which means it's falling really fast. So that's one of the important properties of your PDF. As x moves away from mu, your y reduces exponential of squared. So x squared, correct? Now let's understand what this fall actually mean with a simple example. Let me write the third conclusion. My third conclusion is, as x moves away from mu, y reduces exponential of minus x squared. Correct? Now let's understand what does this fall actually mean with a small example. So what do we have? We have here y is equal to exponential of minus x squared, right? So let's assume this is my, let's say, x, this is my, let's say, y is equal to exponential of minus x squared. Fine. So let's assume if my x is equal to 0, what is the value of my y is equal to e raised to the power 0, which is equal to 1. Now let's assume x is equal to 1. So if x is equal to 1, what is the value of y? 1 by e raised to the power 1. This value will comes out to be 0.3678. Now when x is equal to, let's say, 2, then this will comes out to be e raised to the power 4, and this value will be 0.018. And when x is equal to, let's say, 3, then 1 by e raised to the power 9, which is equal to 0.000123. So what is the point of explaining you this thing? Let me, if you look at this, my x is increasing and my y is decreasing. But the point here is how much y is decreasing. So here, if you look at this thing, my x here increased only by 2 times. If you look at this, my x here increased by 2x, 2 times. But if you look at this thing, and here my x has increased by, let's say, 3 times. Here my x has increased by 2 times, and here my x has increased by 3 times. But look at how my y has changed. So if you will look at this, you will find that if you will divide this thing by this, you will find that this has decreased by 20x. And if you will look at this, how this has changed, so this has changed by almost 100x. 100x. Fine. So can you see, when my x is increasing by 2 times, my y is decreasing by 20 times. When my x is increasing 3 times, my y is decreasing by 100 times. So this is a crazy high difference, right? That's what I mean when I say exponentially quadratic drop. So this was, so if it would have been an exponential drop, it would not have been this severe. So the shape of your Gaussian distribution is, it falls exponentially quadratically. Shape of Gaussian distribution falls exponentially quadratically. That's all for the day. See you in the next session. Keep learning, keep smiling.